So Nati, have you decided already what you're lecturing on at TASI?
Not really. Why?
I don't know, because I think you're also in the first week, right? And they asked me to do some, so I assume you will do either generalized symmetries or some.
No, I actually think I'll do symmetries and anomalies on lattice systems.
Right. Okay.
So no higher form symmetries.
Cool.
To really bore everybody with these details. So everybody's eager
No,
to
I think
know.
it's great for students, right? It's supposed to be.
No, I'm talking about the audience here now.
Sorry? Oh, you don't want to bore the audience here now. Okay. Right. And I think Andy wants to probably get started. So
all right, yeah. Are you ready, Sakura?
I'm ready, yes.
All right, so welcome everyone once again to the WHCGP. Today we're delighted to have Sakura Schafer-Nameki, who will speak on theta defects and non-invertible symmetries. And if you have a question during the talk, just feel free to unmute yourself and speak out. So thanks. Take it away, Sakura.
Great. Thanks very much for the invitation. So the first time I spoke at the WHCGP was in 2020, which I think was a peak of the pandemic. And that was when we sort of uncovered one-form symmetries or higher form symmetries in 5D theories. And that was really sort of the starting point to develop some of the things that I'll talk about today. But so, we've come a long way. And today we'll talk about vast generalizations of the kind of concepts that I actually mentioned back then, which were very specific to string constructions in 5D. Anyway, so today's talk is based on a few papers in collaboration with my postdocs, Lakshya Bhardwaj and Jingxiang Wu, as well as my student, Leah Bottini, and also condensed matter theorist, Apoorv Tiwari from Stockholm. And if I get at the end to something more string theoretic, it will be with Fabio Pruzzi from Padua, Ibu Ba from Johns Hopkins, and Federico Bonetti from Durham. And it's appeared in these papers. And so if you want to pick out one that actually covers a lot of the things that I'll discuss today, it's this paper from December last year. And as Andy said, please ask questions whenever you have any. So I think we all sort of, I don't know how many people in the audience are following the field very closely, but it's undeniable that there's been sort of a symmetry revolution, and sort of a very, very crude measure is look at this very famous paper by Nati and collaborators, and its citations in the last few years have just sort of exploded. And one of the really big reasons why this has happened is that in the past year or so, we've uncovered certain symmetries which are a little bit unusual in quantum field theories, in particular in 4 dimensions. And these are these so-called non-invertible symmetries, and I'll discuss in detail what exactly this means, how they fit into this generalized symmetry framework. And you'll see there are like loads and loads of papers on this topic. And I mentioned here a few that discussed in quantum field theories. So I'll just start with a very broad introduction on what are actually these generalized symmetries and where these non-invertible symmetries fitting in. And so the insight from this paper here is we should really think of topological defects in quantum field theories as symmetries. And this insight, or just this proposal, actually led the authors to actually, first of all, generalize standard, say, global symmetries like flavor symmetries to so-called higher form symmetries. So p-form symmetry groups act not on point-like objects, but on charged p-dimensional defects. And their charge is measured in a d-dimensional spacetime by a topological operator that links with a p-dimensional defect. So that's a codimension p+1 topological operator. So always label defects by some dimension. This is the Q here is the dimension of the operator. And then there's some group label. In this case, it's a group label, but we'll see later that these labels will be much more general in these non-invertible settings. So here G is an element in a group, usually a finite group. And these sort of compositions of defects, if I take two of these topological defects, put them into some kind of correlation function, that should be equivalent to actually putting in the defect that's associated to the product. So G and H should give rise to G times H. So that's what we usually would call a group-like symmetry in a quantum field theory. So these higher form symmetries are acting, the generalization is they act on these higher dimensional defects, for example, line operators, etc. But in fact, they're still group-like. There's sort of a mild extension of this when you have several higher form symmetry groups. Then you can have sort of either a direct product of the 0, 1, 2, and so on higher form symmetry groups, or you could have a slight extension in the sense that the p-form symmetries may form not products, but so-called higher groups. So an example is a two-group symmetry when for example, the 0-form symmetry acts on the 1-form symmetry non-trivially. But there are many more extensions of this. I don't want to really talk about this today because the focus should be on these non-invertible symmetries. So here we actually, for both of these cases, the symmetries still had these kind of compositions that were group-like. For non-invertible symmetries, this is now sort of the thing that we relax. So very roughly speaking, going from groups to algebras. So if you fuse two of these topological defects, this doesn't actually give sort of a single defect that then has some very specific relation to A and B in terms of multiplication or group, but generically you get a sum of defects, topological defects. So here Q is fixed, the dimension of this defect, but then actually there's a sum of these on the right-hand side. So this is non-invertible in the sense that generically, if you have a defect like this, you will not find another one such that you get the trivial defect on the right-hand side. So this may seem somewhat exotic, but in fact, perhaps surprisingly, these are quite ubiquitous in sort of high-dimensional quantum field theories, and in particular, for example, in 4-dimensional pure Yang-Mills theories, we have these non-invertible symmetries. The sort of nice aspect about these generalizations has been also that there's sort of a science sociological bonus that really there's been a lot of exciting connections between high energy theory, high energy phenomenology, applications in pheno about this, condensed matter, and also in mathematics. So hopefully, if there is a part of the audience in some subset of these, you get something out of this talk. So what are examples of these non-invertible symmetries? Well, the easiest examples are very well known so-called Verlinde lines in rational conformal field theories. So you have topological line operators, and their fusion is given in terms of the fusion coefficients of the RCFT. And these we can calculate using the Verlinde formula. And so these are actually very well known, very well studied in rational conformal field theories. And the labels, these labels I and J, are basically the primaries for this conformal field theory. So in 3 dimensions, there's a vast class of non-invertible symmetries in the sense of modular tensor categories that people use to classify topological order. But the focus today will be on sort of 4-dimensional applications or quantum field theory applications where we have symmetries acting on not necessarily topological quantum field theories. So the first example was really this O2 gauge theory, where we obtain it by taking U1 and gauge charge conjugation. But then this is literally just a kind of outer automorphism. And we can also generalize this and actually formalize it somewhat more. The diffusions in this initial paper were somewhat, they looked peculiar, and I'll get to that later on, that in these these non-invertible symmetries, the fusions, if you are not using the right sort of framework, you might actually get sort of fusion of topological defects of, say, dimension D to fuse into defects of dimension D-1 or lower dimensional. And that seemed confusing in this paper, and that actually sort of kickstarted some of the discussions later on. So more generally, you can gauge outer automorphisms of pure gauge theories in 4 dimensions, and that gives non-invertible 1-form symmetries. So in this case, the outer automorphism acts, say, on the 1-form symmetry, And by gauging, we get non-invertible symmetries. And then there are, of course, these very famous duality defects now where we gauge sort of a self-duality. There's a self-duality in a theory, and there's a non-invertible defect that generates a non-invertible zero-form symmetry. So those are examples, and I'll expand on these later on in the talk. But that's to give you an idea of what type of theories you could expect these sort of symmetries to appear. Now, the really interesting question for physicists is, of course, what's the utility of these symmetries? Of course, for higher form symmetries, there are many interesting applications at this point in time already, but for non-invertible symmetries, what exactly can we infer from them? And I think it's clearly very early days. But in 2 dimensions, it's very nice. You can use them to constrain, for example, the existence of gap phases. So, for example, the number of vacua is constrained. So if for example, your symmetry category, or in this case, the symmetry has an easing subsymmetry, then you can constrain the number of vacua to be a multiple of 3, for example. So these are very powerful sort of theorems you can prove using these types of symmetries. In 4 dimensions, of course, there's very nice applications of the one-form symmetries to confinement, deconfinement. And there are many interesting sort of new observations about the non-invertible defects, for example, in pure n equals to 1 super Yang-Mills series. And many, many applications in pH, neutrino masses, non-invertible symmetry breaking, generating sort of small neutrino masses, pion decay, etc. And of course, also applications to the swampland. In fact, this initial paper was a swampland paper that was about the completeness of the spectrum if you had some non-invertible symmetry like that. So there are many directions in which this can sort of have interesting applications, but I think we are still very much trying to understand how to characterize these symmetries. Okay, so I keep saying, I'm trying to hold back saying the word categorical, but really, how do we go from non-invertible to categorical? Well, I think there are some, at least in the physics, I don't know whether the audience is mostly physics or mostly math, but there's certainly some resistance in the physics community to sort of categorify certain things. And I think here there's a really strong case that we have to use categories. This is the framework to understand symmetries. And so I'd like to sort of expand a little bit about this. So if you have a quantum field theory in d dimensions, and you have topological defects of various dimensions, so they all generate symmetries, then the question is, what's the framework to actually characterize these? So if you start with a standard zero-form symmetry, there's obviously, everyone says it's a zero-form symmetry group. We have group theory, and then we study representation theory, and there's absolutely no doubt in our mind that this is the right framework. And there's sort of an interesting, nice little historical note that this actually wasn't always the case. And so actually, according to Wigner, from some interview in 1981, Schrödinger really coined an expression called the Gruppenpest, which is like the group pest, saying that group theory really should be eradicated and it's just a mathematical formalism that should be abandoned. And it's not going to add anything to the physics. So in some way, you could make a case that maybe categories seem to be a huge formalism and an expansion compared to just a group theory and representation theory. But given a quantum field theory in d dimensions, you have topological defects of dimensions 0 to d minus 1. You can ask, what's the structure? And in fact, what seems to very naturally emerge is that you have a higher fusion category. And one reason why that is the case is that non-invertible fusions basically take you immediately out of this group theoretic framework. So this is sort of a higher categorical symmetry, a case for these kinds of structures. And basically, so the slogan should be, we should really stop worrying and start loving categories. And I think this movie anyway has a very interesting current sort of relevance. Anyway, so what do I mean with categorical symmetries? Higher categories play so a similar role to groups and group representations. A fusion P category has the following layer structure. So we start with these DP, so these are p-dimensional topological defects. So these are sort of the top layer in this P category. And then there are one morphisms. So you have between two p-dimensional defects, a p-1 dimensional topological defect. So this is like an interface. And then between two of these p-1, you have a p-2 defect, and it has this sort of layer structure. So for two fusion category, we can think of this as we have topological surfaces. These are the top layer, these are the objects. Then there are topological lines, which are the interfaces between two-dimensional topological surfaces. So these are the one morphisms. I can have two different one morphisms between given objects, D2A and D2B. And then between these two one morphisms, there can again be two morphisms. So these are now point-like objects, or point-like topological operators, and that are the two morphisms. So this is in the two category case, the type of layer structure that we'll be looking at. And I'll give you very concrete examples of that in the following. And in addition to this sort of layering structure, we want a little bit more. We want a monoidal structure, so loosely speaking, some type of structure to take fusions. And fusions not only of the objects, so the top layers, so this is just this non-invertible fusion I was showing you earlier, but on each one of these topological defects, I will have now these interfaces, and there'll be also fusion of these interfaces defined in this category. And as you can sort of tell, the higher the category is, the more layers it has and the more complicated the structure becomes. Already here, this fusion of these one morphisms is, you have B1 CC prime. So this is basically a defect here that can appear between the surfaces that appear in the fusion of A with B and A prime with B prime. Okay, so that's very roughly what these higher categories are. And I'd like to now give a very physics-motivated construction of such defects. But maybe I should just pause whether there's, from this introductory part, a question about this very sort of broad brush introduction. Jack.
I have a question. So there's a notion of strictness. Are these sort of strict N two categories or whatever? Now, is the composition of
if you tell me what strict means, I will tell you whether they are.
No, I'll tell you what it means. So it's whether the composition of one morphisms is associative or only associative up to two morphisms.
Yeah, so it can also be just up to two morphisms. That's right.
So that would be a weak two category, I guess.
I think that's quite
correct.
So there are many, many such disclaimers or sub definitions of fusion categories and then also of higher fusion categories. So the ones that I will actually be studying are very simple. They'll be just things like higher vec, so higher vector spaces with some group symmetry, so higher vec of G, and then representations, so 2-rep of G, etc. So I think in those cases, actually, the fusion will just compose without this, but I don't see a reason why it doesn't have to actually close up to a two morphism. Okay, so what I would like to actually do is motivate these from a very physics sort of perspective. So if you haven't actually thought about higher categories, this is a very natural way they will appear. And these are the so-called theta defects, and they're called theta defects because they are generalizing theta angles. And theta angles are, of course, in four-dimensional U1 gauge theory, we have sort of this kinetic term with gauge coupling, and there's a theta angle, theta f which f. It's a very simple theory, and I can think of it in the following somewhat strange way, but this is sort of what we'll generalize in terms of these theta defects. So I can start with a completely trivial theory, which has a global U1 symmetry. And all I will do is I'll simply start with this theory that has a trivial U1 action, a U1 global symmetry, but I actually allow myself to have also what's called a U1 SPT. So the symmetry protected phase, which is precisely a coupling theta f wedge f, where this is now background for this U1 global symmetry. So I start with a trivial theory plus this SPT, and now I gauge the U1 symmetry. I could have also just started with this trivial theory and gauged a U1 symmetry, and I would get just this, this is just the kinetic term for the U1 gauge field. But as I include this theta, I get the full sort of T mod U1 theory is now gauge coupling plus this theta. So I want to think of this as I've added on top of this theory an additional sort of SPT phase and then gauged at the same time. So stacking with a U1 SPT, engaging then corresponds to adding a theta angle. So what I'd like to do is now generalize this somewhat, you would never think of this in this way perhaps, but you can think of the following as a generalization of, or an extension of this idea. So I'd like to start with a theory in d dimensions, has a zero form symmetry, and I always think of this as a finite group symmetry. And now we essentially sort of take that theory and take a product with a p-dimensional TQFT and then gauge a G. So this p-dimensional TQFT I assume to also have a zero form symmetry, the same zero form symmetry G. And then I gauge a diagonal G. So take the product of the theory with this p-dimensional defect. This is sort of a product theory. Both have a G symmetry. And then I gauge G. What happens is that this p-dimensional defect now is actually part of the theory. It becomes a topological defect of this theory of the gauging. And in fact, this is one way that almost all the known non-invertible symmetries actually can be thought of. Some sort of generalization of this. And the key is that these defects in this theory, in this gauge theory, in fact, will have generically non-invertible fusions. So just to warm up, I like to discuss this in 2 dimensions. And so in 2 dimensions, we know very well Apoorv folding. So you start with a 2D theory with a zero form symmetry, G. That's generated by topological lines. And so topological lines are just D sub 1 with a G label. And the fusion is group-like. So D1G, D1H is D1G times H. So what, from a categorical point of view, you would call this is actually just the fusion category for back G. G is a finite group, and you take G graded vector spaces, but effectively this is all there is to it. So now I'd like to gauge G. So there's a theory that has the zero form symmetry. So gauging means either in the sort of generalized global symmetry sense, I now insert a mesh of topological lines, and then sum over all these background configurations, and that will give me sort of the gauge theory. One thing I need to be careful about is, in fact, if I'd like to determine what the symmetry of the gauge theory is that now the topological lines of the gauged theory will have to be compatible with this mesh of topological lines that I inserted and summed over. So in fact, what I have to actually ensure is that when I look at the lines of the new theory, they have to be sort of blind. They have to sort of be able to move through this mesh. So concretely, this means if I have a topological line in this gauge theory, then it needs to be sort of compatible with either ending the lines or fusing, or so this picture needs to commute. I either end them or I fuse them and then end them on this line that needs to sort of commute. And this is sort of the left action, and there's also right action. In fact, what this means is it's sort of what's called a bimodule condition on this. So these lines in this gauge theory are sort of compatible with the left and the right ending of these topological lines. So in fact, these D1G lines have to be invisible to the lines D1, and so this is then what will generate the symmetries T mod G. So mathematically, this means actually we have to pick an algebra object in this category C and then solve sort of these bimodule conditions, where this algebra object is the sum of all the topological lines in vec G, and the bimodules are then simply the rep G category. So these are just the representations of G. So this approach generalizes, but you probably have questions about this because it's very fast. The point is, this is sort of how you can very systematically try to generalize this to higher dimensions, but there's a much more natural way, and this is what I'd actually like to talk about, which is these Theta-defects. And they're equivalent to this sort of inserting the mesh, ensuring that these lines are compatible with it, and then finding these bimodules. Okay. So how do I actually think about this in an alternative way? Well, this theory with the zero form symmetry in 2 dimensions has these topological lines. And in fact, we said this category is like G. So gauging, sort of in a physical sense, would be you actually have a dynamical G gauge field now, and you can introduce now Wilson lines in some representation R of G. So you can write down D1R is trace R e to integral A. And in fact, these will just fuse according to how these representations decompose, right? So the tensor product. So in fact, from this perspective, you also would see that the lines, these dual sort of symmetry generators also form some kind of representation category of the group G. For abelian groups, in fact, this is just going to be, again, the same as isomorphic to the group itself, or to vec G. But for non-abelian, this is not necessarily the case. So this is another way of seeing what I explained with these bimodules, that from vec G, after gauging, you get rep G. And now I'll actually explain it using the theta defects. So we said we can start with the 2D theory with a finite zero form symmetry. So this is this symmetry category vec G. Now I'm saying, okay, we can stack 1D QFTs, which have G symmetries, and then gauge G. And the resulting theory will then have additional topological defects, which come from these GT QFTs. And these will be precisely these D1R, where R is now a representation of G. So in fact, before I can tell you this result, that it's actually really giving you rep G, right, the first question you should ask is, what actually are the GT QFTs? Well, they're just simply characterized by the number of vacua these have, and then the action of G. So I have a number of vacua, and then G acts on it, so they'll be exactly in representations of G. And so this is how you see also from this perspective that these lines actually will form the rep G category. So the symmetries of the gauge theory form rep G. So this is the story in 2 dimensions. And now we can take this to higher dimensions. So this was sort of just revisiting things we know very well from gauging zero form symmetries in 2 dimensions. From this theta defect perspective, now we can take that to higher dimensions and actually say, well, I have a theory. I have a G symmetry. I can stack on top of it a GT QFT and then gauge the diagonal. And what I generically will get is a whole D-1 category, which is actually D-1 rep G. So there's a slight subtlety here about what exactly this rep G is, but for 2 categories, I'll go through this now in detail. And there are some interesting effects in 3 rep that are actually due to the fact that when you stack 3D QFTs with some G symmetry, they can in fact also have a non-trivial topological order. And so you can generate somewhat, so the effect is actually somewhat different from in the case of two reps. Okay, so, right, you can also do this with higher form symmetries, you can stack with SPTs, but I'll stick to zero form symmetries, and let's do an example just to see this at work.
Sorry, the definition of the higher rep G category went by a little fast. Could you?
Yeah, so I will actually, so this is essentially simply constructing a version of rep G, and for 3 rep, ask me at the end again, because for 3 rep and higher, what you can stack here is in fact also, for example, U1 level M Chern-Simons theory. Depending on whether your theory actually has an anomaly or not, it has, say, a 1 form symmetry, has the U1 level M Chern-Simons theory, isn't just characterized by number of vacua and representations of G. So there's a sort of another level, and we'll call these twisted theta defects. But if you're just stacking with GT QFTs, which are characterized by number of vacua and the representation action of G, and potentially some kind of co-cycles, then it's an object, the objects are D-1 dimensional GT QFTs. The morphisms are junctions of 2 of these. So these are D-2 G interfaces between TQFTs, and so on. And we'll see it in the 2-rep case very explicitly. And for the 3-rep, I'll give an example that shows that it's not just this, it could be a much vaster class of TQFTs that you can actually include here. Okay. So for 3-dimensional gauge theories, one very nice example, or the class of examples that are extremely sort of rich for these non-invertible symmetries and generally for studying these categorical aspects, are the orthogonal gauge groups. And if you look at PSO4n, this is basically you start with spin 4n, you simply connect the gauge group, and you gauge its center. And why is this a nice gauge group to look at in 3 dimensions? Well, it actually has a zero form symmetry, which is purely, so it only has a zero form symmetry, and actually it comes from the dual symmetry of the center, and there's also the outer automorphism action. So if you actually look at the symmetries of PSO4n, these are D8 elements, so the dihedral group D8. So Z2 times Z2 semi-direct with Z2, where the Z2 acts by exchanging these two Z2 factors. So what the symmetry actually category of this is again, just vector spaces. You have topological defects, which are 2-dimensional defects, which have group-like fusion given in terms of a D8 group multiplication. So these are the D2Gs. And then on each of these topological surfaces, there's a line, and they will just fuse along with these surfaces and so on. So it's a completely invertible structure. And this is what mathematically you would call 2-vec D8. And what I'll explain in the following few slides is when you gauge the D8, what you get is what's called 2-rep D8. And in fact, this is now a non-invertible symmetry. So going from this PSO4n, which has a pure zero form symmetry, to the gauged version where you gauge the D8 group symmetry, you get to actually the pin plus 4n, and then has a 2-rep D8 symmetry category. So just to give you this picture, so spin 4n, we gauge the 1-form symmetry, we go to PSO. This is a purely invertible 2-vec D8 zero form symmetry. And now I'm gauging the D8, and it gets us to pin plus 4n, and this is now a non-invertible symmetry. And I'll explain now what this 2-rep G precisely is.
I have a very lowbrow question.
Yeah.
From so in the end of the day, you have some group, some gauge group, pin plus or 4n, regardless of how you created it in steps, but that's what you have.
Absolutely,
right?
yeah.
Okay, so if I didn't know of the whole stuff, I would just say, okay, I have some group, so I have some gauge theory, and it has some electric and magnetic symmetry. And why is it non-invertible?
So I think you would start trying to compute the fusion of these defects. And say you would, in this case, you would ask yourself, well, if I compute the diffusion of topological defects, you would see that, presumably, assuming that these are invertible, so these would have 1-form symmetries.
Are you talking about electrics? You're in 3 dimensions. Are you talking about electric? These are electric symmetries, right?
Yeah, so here I started with basically spin, which had a 1-form symmetry.
Yeah.
And then a 0-form outer automorphism. So basically the outer automorphism is just acting on these two
right.
S and C nodes.
I forget how you got it. So you have pin plus of 4n.
Yep.
That's the gauge group.
That's right.
Okay, and it has an electric 0-form symmetry.
Well, so this one doesn't have any more 0-form symmetry. This is sort of the point. I start with a 0-form symmetry.
Okay, good. Thank you. Now you answered my question. Thank you.
But it has a 1-form symmetry. And now the question is, what's the fusion of this 1-form symmetry? And I'll explain exactly how this comes about now. I'll first do actually Z2, and then 2-rep Z2, and then we'll see also this example of the pin plus again. Okay, so we're in 3 dimensions, and so what we have is fusion 2 categories. the top layer is two-dimensional topological defects. So they generate in 3 dimensions the zero form symmetry. Then one-dimensional topological defects, they generate sort of the next layer down, and then the zero form symmetry, the topological local operators. They're the two morphisms, and they appear as these junctions. So now the question is, how do I actually get these types of fusion categories appearing in quantum field theories? And again, there are two ways of doing this. One is this looking at, background, you put G background. So we start with a G symmetry, invertible group-like zero form symmetry. We put a mesh of topological defects, now surfaces, and we need to ensure again that there's sort of this compatibility of fusing first before we reach the surface or after. So there's some kind of bimodule category algebra going on, so that you should be looking at bimodules for algebras in two categories. I don't want to discuss this because this will not be very insightful. This is one way, and it's equivalent to what I'll tell you in a moment. So the way we'll actually construct them is stacking GT QFTs and gauging the diagonal G. And that's actually, we can prove that these are sort of equivalent descriptions. So again, the philosophy is we start with a two-dimensional GT QFT now. So what are 2D QFTs? Finite Riemann vacua modulo some Euler number counter term that basically characterized again by some integer, which is the number of vacua, and then the group action. So in this case, the 2D QFTs that have a group G symmetry are basically given by their n vacua, and then there's a local basis, which has sort of a very simple kind of local operator fusion. I and J will fuse to delta ij I, and then there are also interfaces between them. So here these I's are essentially, if you have some surface D2I, D2J, then this is Ij, and they have a composition. These topological lines.
Sorry. I mean, it might be a trivial point off of the main point of your talk, but I think there's a little more data. First of all, the 2D TQFT that you're assuming here is semi-simple.
That's right. Yes.
And secondly, there's Frobenius data. There's a trace on what you're calling the identity object.
Yes, I agree. But here I'm not actually. This is literally just a trivial 2D TQFT. I literally just have the vacua, and I'm going to, on top of that, define a group-like action. So there's sort of a grading by group. So I'm defining a fusion two category, two vec, which is essentially two vector spaces, which is defined in this way.
So is this going to be equivalent to a Turayev algebra? So a 2D TQFT is equivalent to a commutative Frobenius finite dimensional Frobenius algebra.
Yes.
So a G 2D TQFT.
So here there's no G yet. I will add the G in a moment.
I know.
But here there's basically this is just two vec.
Yeah, I'm looking ahead. So I'm going to be wondering what's the relation to Turayev algebra.
So I think the fusion is simply given in terms of TN-TM is TNM. It's sort of what maybe the simplest possible Turayev algebra is that you can think of. It's just characterized in terms of n vacua, and there's some very simple fusion on these 2D TQFTs. They're basically given in terms of sort of n times the trivial theory. And on top of that, I define diffusion in this way. Greg, is this something you can?
Okay, I'm following what you're doing.
All right. So now the question is, when I add the G action, what is now the structure? So before, remember, when we did this in one dimension, we had the GT QFTs were essentially, again, vacua, and at a group action, you decompose these n vacua into representations, in irreducible representations. So 2D GT QFTs, the ones that have a single vacuum, you can still on top of that add a GSPT phase. So that's sort of the new piece. And a GSPT phase is just an element in H2 of GU1. And then, in fact, if you have multiple vacua, you can have also spontaneous symmetry breaking. So G could be broken to a subgroup H. And so essentially the minimal set of GT QFTs from which we can construct all of the other ones are given in terms of specifying a subgroup G and then one of these SPT phases. And then I can take linear combination of these TQFTs, and that's basically all possibilities. And each one of these has sort of that many vacua. Okay, so in terms of these topological defects, right, what you'd like to do is we take these 2D GT QFTs, we stack these on top of our theory, and then we gauge the diagonal G symmetry. So what actually does this entail? Well, it means that these TQFTs now become topological. They get promoted to topological defects, labeled again by subgroup and an SPT phase. And now we can compute a fusion, and this is sort of twisted Burnside type ring relation, or we can also just look at sort of the vacua and the action of the symmetry on these vacua. And this is the fusion of the topological defects. In the paper with Lakshya and Jingshang, we also work out the fusion of the one-dimensional interfaces and the local operators. But this is sort of the key. You can see already here that there's a direct sum now. If you have subgroup H, subgroup K, so if symmetry breaking to subgroup H, symmetry breaking to subgroup K of G, then you're summing over these double cosets of topological defects of this type. And there's always sort of a condition on also these cocycles that they're compatible. Okay, so let's do an example. Let's look at the simplest possible group, G. In this case, we have two subgroups. One is the trivial subgroup, one is Z2 itself, and there's no SPT phase. The SPTs start being interesting for Z2 times Z2, for example. So the objects are labeled by the subgroups in this case. So one is H equals 1, the other one is H equals to Z2. And so this one is a TQFT with 2 vacua, and the other one a TQFT with 1 vacuum. And now we can sort of just either use this general twisted Burnside type relation, or just look at how the different vacua are tensor product. So for the single vacuum with itself, there's just a single vacuum. So D to id with itself becomes D to id. Then for the fusion between D to id with this non-trivial defect D2 minus, again, there's sort of 0 is this trivial guy, and then there are these 2 vacua for this non-trivial one. Again, there's a 1Z2 orbit, so I actually get 1 D2 minus. And then the interesting fusion is the one where we fuse 2 of these D2 minuses with each other. And they're basically the 2 Z2 orbits plus plus minus minus and plus minus minus plus. And so we get 2 times D2 minus. And that's now an example of a non-invertible fusion, because you get the defect fused with itself is 2 times the defect. And this actually, this category, you also look at the morphisms and 2 morphisms. This is what mathematicians would refer to as 2-rep Z2. So we started with 2-vec Z2 in this case. So this is just vector spaces. So this actually didn't write it down, but this actually would be, we start with the theory. So we have a G symmetry or 3D theory, a zero form symmetry. And this category is 2-vec Z2. And we gauge the Z2 and we get to 2-rep Z2. So now the question is, what is this defect here? And in fact, if you followed the literature on these non-invertibles, these D2 minus defects are precisely the condensation defects of Umbridakis, Saif-Nashri, and Shao. So what are condensation defects? These are topological defects that are obtained by gauging a symmetry on a subspace. And in this case, it's basically this D2 minus is the trivial topological defect, where we gauge the dual symmetry. So this is the symmetry this is D1 minus is the generate of the dual symmetry to the zero form symmetry. So there's a 1 form symmetry generated that's gauged on a 2-dimensional surface. So you should really think of D2 minus as a surface where there's a mesh of D1 minus inserted. And more generally, these D2H alpha H are actually always the 1 gaugings of H inside the dual symmetry, which is a one-form symmetry. So this is actually, so Nadi, this is basically one way of seeing this category does not have any non-trivial topological surfaces that are not condensation. So they're always either the trivial surface defect or the trivial surface defect where you inserted, you gauged on that subspace the one-form symmetry. So REP Z2 has this sort of structure. Yep.
In that example, is there any way to tell that the bulk theory is three-dimensional and not higher dimensional?
So here, it's true. So I could have also said this is a two-categorical subsymmetry of this, of a much more complicated category, right? But I'm gauging zero-form symmetry, and then I'm getting sort of, these topological lines. So that's where I actually put it in. But you can also, of course, a two-fusion category can be the symmetry, also of a much higher dimensional theory, but then you're just describing sort of the surfaces and the lines. But the gauging is making it, I think, very manifest that you're looking at a three-dimensional theory. Okay, so the structure of this, is there another question? No? Okay, so the structure more generally is we get two rep G whenever we gauge a theory with a G zero-form symmetry in 3 dimensions. And in the math literature, you'll then find that the objects, which are, this is the trivial defect, which is just the identity surface defect. This is this condensation defect. You'll see these as sort of the vertices of some diagram. So these are the objects. And then between them, each one has a morphism, rep Z, vec Z. Right? And then they're in between these intertwiners. And these pictures can become arbitrarily complicated, if you like. And actually, the most interesting sort of simple case to look at is when the next simplest case, is when the group is Z2 times Z2, when you actually get also non-trivial SPTs.
Sorry, some of these arrows should be one morphisms and some of them should be two morphisms.
So here, actually, I'm just drawing, this is basically a one morphism. And then this is basically an intertwiner. You can also now, of course, do something like this if you want to. But it's kind of trivial because it's just vec and vec.
So all the arrows are one morphisms.
Yeah. But right, these are topological. In this case here, this is just a topological trivial line on D2 id, and then of course, if you have D2 id and D2 minus, you can have some interfaces I id minus, and these are these guys here. Yeah, these are one morphisms, and then if you wanted to, you can also then draw pictures where the two morphisms are in, and then you might start putting in these diagrams. That's, I think, what also someone else was asking about before. I think Jack. Okay.
So sorry, a silly question maybe, but I guess I can't quite tell how you know what the fusion rules are in the higher fusion rules. And
here,
like you had Chern-Simons, right? Chern-Simons has Wilson lines. Their fusion algebra is not that of rep G.
No, because it's not obtained by gauging an invertible symmetry necessarily, right? So here I'm starting from something that is a gauging of an invertible symmetry. And in fact, in Chern-Simons, and I'll get to Chern-Simons in a moment, right? This would be when you have actually topological. So we'll get to an example where Chern-Simons becomes relevant, where in fact you also don't have this very simple sort of description of GT QFTs, which are all simply sort of trivial vacua with some G action, maybe an SPT. So
I guess one way to ask that question in a finite group case is what if when you gauge, you add a cocycle as you would in Digraph-Witten theory in the bulk? Does that modify?
So you can, for example, add a term like a Toft anomaly. And in fact, that can be very interesting because the Toft anomaly, when you gauge, it could be a mixed anomaly. If it's just a Toft anomaly for the symmetry you're gauging, you can't gauge. But in fact, if you actually have, say, a mixed anomaly, this can lead to interesting, say, two groups, higher groups, or also non-invertibles. I'll give an example of that in a moment also in the four-dimension case. So I don't know whether this answered your question. I don't think so.
I think so. Thanks.
Okay. All right. So okay, in terms of time, sort of have 10 minutes. So this is sort of now the three-dimensional picture we discussed, going from well, this is a simpler version of this here, where we gauge from here to here, but now you can see very similarly to that, this 2-rep D8 comes about by exactly carrying out this general procedure, looking at these QFTs, symmetry breaking plus SPT phases, and the fusions are just encoded in this
picture that you had before, the one with the arrow. When you went back to keep going. No, in the other, I think it's the other direction. The one when you had the pin 4.
This here?
The same. Okay, this one, but also the one that you had the same thing.
I had the same one. I added another node. Yes, this one here.
Right. So here I wanted to ask. So again, imagine I didn't know all that. So somebody handed me pin 4 gauge theory, and I would have said that the electric one-form symmetry is just the center of the group. And I guess you're going to tell me that that's not the whole story.
That's not the whole story.
Yeah. And where exactly would I go wrong?
So I think you would try to calculate. So first of all, you would perhaps, you start with a theory that has a D8 zero form symmetry. I know you don't want to start with gauging, but that's one way of seeing it, right? When you gauge and you have a non-abelian group here, you're almost certainly going to get something non-invertible on the other side. So I think if you started here, computing diffusion, assuming these are invertible, then I think at some point, so I think you would probably not be describing the correct. So for example, one way of seeing it, you could gauge back to a spin for n, which is just gauging one form symmetry as E2.
Yeah, but you're too much tied to this example. So if I just looked at the center, I would get some symmetry and it would be abelian, I guess. And is the statement that there is more to it, or that I did not identify the full electric symmetry? What would be the mistake?
Yes, I think the statement is you did not identify the full symmetry of the theory.
I see. Thank you.
Yeah. Greg, I think you also had a question. At least I saw you on mute.
That was an accident.
Okay. So we have in this three-dimensional web these global forms, and indeed you have in both of these cases these non-invertible, so pin plus and also PO, which is obtained from PSO by gauging the one of the zero form symmetries, this auto-automorphism zero form symmetry, non-invertibles. So in this case, this is the representation 2-rep of this D8 group, and in this case, there's actually a 2-rep of a 2 group. So the 2 group here is where you have the 1 form symmetry, and you have an action of the 0 form symmetry on the 1 form symmetry. Okay. This can be generalized to higher dimensions, and here there's sort of a disclaimer I need to make that indeed you have to be careful when you're stacking these TQFTs in higher dimensions, that there's sort of a much richer structure, and I'll give you an example of that in a moment. But very generally, you'll see in D dimensions that you have, again, the PSO, which is basically some back of a 2 group, and then we can start gauging and filling out this full categorical web. And indeed, it seems very complicated. You start somewhere here and you go from here to here to here, and you can get all these global forms, but surely there has to be a much better way of actually characterizing this. Actually, there's a question or comment by Dan Fried, orthogonal lead groups and actually 2 groups which incorporate both the center and the auto-automorphism group. Excellent gauge theories. Okay, yes. Dan, did you want to, I don't know in what relation you made this comment.
I think that's a way to see. It was just a comment on what Nati said, that it's a way to see that there's often more than just the center. The outer automorphism group also enters.
Yes, but I think Nani would say also,
No, if I may say
spin,
what I meant,
there's also a zero
I'm
form
right that-
outer automorphism group that acts, right? And you would also say this is a part of the symmetry, but in this case, the zero form symmetry. And what this now becomes actually part of this non-invertible symmetry. That's another way of saying it.
So I'm like to understand that better. So I understand that the automorphism gives us a zero form symmetry. So that I would have known with old-fashioned methods. And
this is here, right? So in spin, everything is still invertible. So spin 4n has, as in 3D, has Z2 times Z2 one form symmetry. That's just the center. And then you also have the Z2 zero form symmetry.
Okay, that's the part I understand completely.
This is completely, everything is invertible. The Z2 exchanges these two. That's the outer. And now what all we're doing is we're gauging this outer automorphism. That's one other way of saying it. So this is this arrow here. And now what happens, very sort of, I call the generators of these D1S and the other one D1C. Then D1S and D1C are not invariant, right? Because they're exchanged. But what is invariant is sort of, morally speaking, D1S plus D1C. And now, even in this spin theory, when you look at this generator, D1S plus D1C, which generates this sort of, you know, it's you would normally not look at this because you would look at D1S or D1C or the product. These are all invertible symmetries. These topological lines, this sort of sum of topological lines is not has a fusion that's now not invertible. And in fact, in this category in pin plus 4n, the fusion of this, if I call this your D1SC, is the D1SC with itself is D1, the trivial line, plus D1V. V is the product. So V is the product of S and C. It's the diagonal of S and C. So, and you can see that directly by looking at just in spin 4n, fusing these two, D1SC with itself. That's one other way. So I was now constructing it from here and gauging the full D8, but you can also just gauge the outer automorphism, and that would sort of be the calculation you have to do. Did this make it clearer or did it make it less clear? Okay, I can't hear anyone speaking, but if there is a question, please let me know. If not, we can come back to it at the end. I'm reaching the end of the time, but so at least with Greg and also Dan being here, I needed to get to this point. All these different gaugings are interesting because they tell us how we can systematically get these non-invertible symmetries, but clearly there's sort of a sense in which keep going in terms of these gaugings is an extremely complicated, elaborate kind of construction. And so, of course, we all were drawn into thinking we should really think of this as coming from a single theory. This is the symmetry TFT, which is really sort of the everything everywhere all at once of symmetries. Basically, it encodes all these different global forms, but now in a theory that's a topological theory in D+1 dimensions. And this sort of what's also what Dan and Greg and Constantine proposed in this paper, and we proposed in some string theory paper following some remarks by Dan. So all these different choices of global forms, these gauge-related forms, really should be thought of as coming from a symmetry TFT, which is a D+1 dimensional TQFT that admits some gap boundary condition. So there's a physical boundary condition, and then there's a topological boundary condition, and the different global forms are essentially chosen by picking different sort of topological boundary conditions and then collapsing this interval.
Sakura, when you write your paper, could you please put the topological one on the left?
Oh yes, can I coach you on this? Because Lakshya and I were disagreeing about this, and actually he wants it here, and I want it there, and I will now take your comment as another reason why we should flip it. I agree, we should flip it, but there's been some disagreement about this, and I didn't care enough. So anyway, it's opposite to what is in the Friedmore-Tellermann paper. They have the physical here, the topological there. Anyway, this is the physical boundary condition. That's where the physical theory will live. And then changing the topological boundary condition, slapping this on, will give us an actual global form. So each one of these nodes will correspond to one particular choice of topological boundary condition. And so in a categorical language, this means you start with a symmetry, so one of these two-vec, two-rep categories, and then you construct what's called the Drinfeld center of this category, and that is basically the topological defect of this symmetry TFT. So very roughly speaking, the symmetry TFT of some category C, this can be a fusion category, higher fusion category, for example, is a bunch of topological defects. They can either end on the boundary, or they can end, they cannot end, so there actually is a junction with another topological defect, and this defect X here, which you can probably hardly see, is now a symmetry generator of your theory. And so in 2 dimensions and 4 dimensions, there's several examples by Kaidio, Maureen Zing, and sort of some general structure will appear hopefully soon in a paper that I'm writing with Lakshya. Okay, so let me, in the last -2 minutes, just say one comment, and then I can maybe finish and answer more questions about this. So I made this point that the Theta-defects, where we take sort of GT QFTs of a certain dimension, stack them onto our theory, and engage the G symmetry, that they're a way of constructing interesting non-invertible symmetries. This is sort of what you could call a universal type construction. If you have a G symmetry, you can get in this way universally for any theory with a G global symmetry. This is a way of generating certain defects that then in the gauge theory are the topological defects. So these are the theta defects, but then they're actually generalizations, and they occur when you have, for example, obstructions to gauging. So this is sort of what Tudor was asking earlier. If you, for example, have a Toft anomaly, then in fact you have to twist with something, or you have to stack with something that's a twisted defect. And in 3 dimensions in particular, you can have 3D topological field theories with maybe some G symmetry, and they can have not necessarily gap boundary conditions, like, for example, you want transassignments. And one example is you could start with a theory in 4 dimensions, like pure n equals to 1 superangles, which has sort of a chiral anomaly. In fact, this is sort of the prototype example of that. You have a 2M, Z2M, 0 form symmetry, a 1 form symmetry, ZM. This is for SUM algebra superangles in 4D, n equals 1. And in this case, there's actually an obstruction to gauging the 1 form symmetry because of this anomaly. Basically, the 0 form symmetry generator will transform on the background transformations of the when it's coupled to 1 form symmetry. So this defect that generates the 0 form Z2M symmetry will transform with a phase, which is basically this Pontryagin squared B2 phase. And to actually cancel this, Kaidiamore and Zing proposed one has to now stack a TQFT that actually precisely cancels off this anomaly. And one way of doing this is to use a minimal TQFT. So that was sort of found in this paper by Sin Lam and by Nadi Seiberg. And this is in this case, the U1 level M transaminase theory. And that would be now a twisted theta defect, where we take this D3 topological defect, stack with a U1 level M transaminase theory, and this object is now the defect in the gauge theory, and that has these non-invertible fusions. So as you go to 3 categories and higher, you have this option, or sometimes the necessity, that you actually need to include TQFTs, which have somewhat more properties, like, for example, they're like transaminase series. Okay, so I'm now really over time. I had some comments about the string theory realization, which is very cute, but I will not get to that. I hope I convinced you that these higher fusion categories are sort of the framework that will be very useful to study symmetries generally in QFTs. The one interesting question is, when you have these non-invertible symmetries that seem to be appearing in many, many QFTs, what is actually the analog of representation theory? So that seems to be an important question. And then also, of course, understanding the symmetry TFT to unify all these different global forms. And so that's sort of the open questions. And then there are sort of more stringy questions, but I'm happy to answer questions about that if there are any. Thanks for your attention. Sorry for running over.
Great. Let's thank the speaker.
Thank you. Are there other questions?
Yeah, indeed. If anyone has more questions, just speak out.
Well, if there's nobody else, I always have questions.
Cool. Go ahead, please.
So if we start from an arbitrary gauge group G, do you have a recipe how to find the symmetry? Rather than doing it by step, gauging this, gauging that? That's question number 1. And the follow-up on that, if you have matter fields in some representation of the group, that usually changes the electric symmetry, because these matter fields can screen the charges. There must be a group theory statement. Given a group, that's the symmetry. And when you have representations, that's the resulting symmetry.
Yep. Okay. So first question, do you give me a gauge group? Shall we do this in 3 dimensions, just to be concrete?
Okay.
So you give me a gauge group, and so the first thing I would do is I will ask to have some Lie algebra G. And at this point, what I would do is I would construct the simply connected group G tilde. Right, so you've given me the gauge group. I can go to Lie algebra. I can construct a simply connected group. And
you assuming it's connected, Sakura? Because your pin group was not connected.
Yeah. So, but I think, right, I can still, so now it gives me some gauge group. I can go to the Lie algebra G, and then I start with the simply connected one. Right, so this is like, he gave me maybe pin plus without telling, and then I will go here to spin. That would be sort of the analog of that. And then I think the what I would now do is so the simply connected one will have a very well-defined invertible symmetry category. So this is sort of, I would construct the symmetry category of that, and then of it the symmetry TFT, and then this particular global form will be a particular boundary condition on that. So I would construct it in this way, and then I can also discuss things that are not simply connected. So I think your question might have been, without going through these sort of motions, right? I construct this, then this has some invertible, some 2 vec of some 2 group. And then I construct of that the Drinfeld center, which is a symmetry TFT, and then this here will be a particular different boundary condition of that. That's just the gauging picture formulated in a slightly different way. I think what you're asking is, can you, without doing this, detect instantly what the symmetry category is?
Yeah, that would be a way of phrasing it. But I can also say another way of saying it. Imagine you just start from a finite group, and you don't have all these G and G tilde, etc.
And
I don't know, S5. If I start from S5.
So you have an S3 symmetry, and you, for example, say you have an S3 zero form symmetry or one form symmetry or something. This is what you're asking. So I think in 3 dimensions, if you say you have an S3 zero form symmetry, I know how to write it down. It'll be just some group-like symmetry. And there are different global forms of that. And that's actually an interesting question because S3 is non-abelian. So you actually, whenever you start, for example, gauging this, you will get different potential non-invertible symmetries from that too. So again, I would write it down in terms of a sim TFT. So for example, for S3, you would again write down something like the representations, right? In 2 dimensions, you would just write down rep S3, and in 3 dimensions, you would write down 2 rep S3. So you actually get a non-invertible symmetry in both of these cases. So I think for S3, you would have to tell me exactly, is the S3 actually a zero form symmetry, or is it something that you've already partially gauged, or it's actually fully gauged? But I think it might be possible to also, so if you give me a gauge group, to start looking at all the center, all the other symmetries. But in the end, I think the sort of most elegant way would be to lift it to this Drinfeld center and then looking at it in terms of the boundary conditions, starting with a symmetry that actually is completely invertible. Now, not all symmetries are of this type. So there are all the symmetries that have one particular boundary condition that is completely invertible. Like in this case, it's a 2-vec of a 2 group. So it's just G0 and gamma 0 and gamma 1. There are theories which actually don't have any boundary condition that gives you this sort of invertible symmetry. And those are the so-called intrinsic non-invertibles. And you can get them by, for example, gauging the actual symmetry TFT. So there's one example, for example, from process theories, I think, but then also in the Kaidiomori-Zing paper by gauging the symmetry TFT with now-to automorphism. So those are particularly interesting cases where you have no frame that is invertible. And then this question becomes sort of like, how do you characterize such symmetries? But at the moment, they're constructed sort of by gauging as well. So I think we're sort of exploring all the possible ways of gauging these systems. Anyway, are there any other questions?
And how does the answer change if you have matter fields?
Oh yeah, so matter fields, right? Let me add a page, okay. So when you add matter fields, of course, you will start reducing, even for the invertible, right? You will start reducing the possible the symmetry. So for example, the one form symmetry, if you have matter fields, so you have, for example, if you add spin for n and you add, say, vector matter, you would just get a Z2. So you screen some of these topological defects. And I think already in the invertible case, you will get a reduced, say, Z2 one form symmetry in this case. And then you can also follow this through this process. I don't think theories with matter generally what kind of category, how that affects the categorical symmetry has been explored too much, because the matter usually breaks it to something that maybe not, here it's a Z2. So maybe not that interesting, but there could be sort of a systematic way of incorporating it. This, I think, no problem with that. And one way of thinking about it is, right, in terms of the sort of, right, in terms of the category, one way of thinking about this is then here you have lines. So these are not really, say, Wilson lines, and you have local operators and another Wilson line prime. And then you can also actually put a categorical structure on the charged objects. So Wilson lines have junctions with local operators with other Wilson lines. So if this is, for example, the trivial one, then this Wilson line here is screened by this local operator. And so then it's sort of trivially charged under the one form symmetry. So it could mean that this local operator actually screens this one form symmetry charge. So in this way, you can start thinking about how there's a structure of also layering junctions of lines and local operators on the charge defects. So that's actually one way of thinking about these. And this extends also to surfaces, lines, and operators. I don't know whether this is answering questions, but that's what I know about the adding matter story. Any other questions?
I think Dan has, yeah.
Well, I was just going to take a crack, although I don't know if it's true, at Nadi's question. Just given a pure gauge theory G, what I wrote in the chat is that there is a canonical two group. The automorphism group of that Lie group could be regarded as a two group, where pi naught is the outer automorphism group and pi one is the center. And there's a nice model for that in terms of what are called crossed modules. And I think that should act in a pure gauge theory. And if you have a representation of the group that gives you matter, then presumably there's a sub two group that preserves that representation, and the symmetry must be broken to that sub two group.
So it's basically you start with this, and then you have this two vec of this two group, for example, and this two group now gets partially screened by effects like this. And I think what you're getting is then the representations of this reduced two group.
All right. Are there any other questions? All right. Well, I guess we're about at the end of the time. So let's thank the speaker again.
Okay, thanks very much.
Thank you. That was great.
Thanks a lot for all the questions.
By the way, a quick comment about left versus right, about that figure, what Greg said.